We're from Group B5, and today our topic is about eigenvalue and eigenvectors. So our group member has Zhang Jinyi, Zhang Xinyi, Zhang Qingran, Wu Dandan, and Yang Zhuoyue. This video consists of 5 parts. The first part is basis concept. The second part is characteristic polynomial. The third part is finding eigenvectors and eigenspaces. The fourth part is properties and theorems of eigenvalue and eigenvectors. And the fifth part is particle application and summary. The first part is about eigenvalue and eigenvectors basis concept. This part is about understanding eigenvalue and eigenvectors. We know that matrix accomplishes a mapping from one vector space to another. For instance, a certain vector x1 is mapped to ax1 and another vector x2 is mapped to ax2. In this example, the mapped vector x1 and its image ax1 are not on the same line. However, some vectors remain on the same line after a mapping, such as ax2. These vectors that lie on the same line before and after mapping are called eigenvectors. For such vectors, the matrix only has a scaling effect. Therefore, ax2 can be expressed as lambda x2. Here, lambda is called the eigenvalue of matrix A, and x2 is an eigenvector corresponding to this eigenvalue. We obtain ax equal lambda x, and x is a non-zero vector. Now let's look at this picture. We will flip this picture along the middle line. The left picture is the original one. The vector in both horizontal and vertical directions are increased on it. We flip the picture. Now we flip the picture using the flip matrix. As you can see, the direction of the right vector remains unchanged after the flip. So it's a characteristic vector because the length of vector after the mapping doesn't change. The eigenvalue is 1. This means if the right vector on the left is x1, then the right vector on the right is 1 times x1. Here the 1 is characteristic value of flip matrix. x1 is a characteristic vector corresponding to the eigenvalue 1. The yellow vector after the flip has completely turned white, but still remains on a straight line. So the yellow vector is also a characteristic vector, and its length has not changed. So the eigenvalue is -1. Here, -1 is another characteristic value of the flip matrix. x2 is a characteristic vector corresponding to the eigenvalue -1.
The second part introduces how to find the eigenvalues of the matrix through eigenpolynomial. The problem we need to solve is how to find the eigenvalue lambda of A square matrix A. First of all, the definition of eigenvalue satisfies Ax equal to lambda x. This expression can be transformed into the matrix A minus lambda times the identity matrix multiplied by the vector x equals the zero vector. This is a homogeneous linear equation system. It must have a non-zero solution and must satisfy the determinant of A minus lambda equal to 0. When this determinant is expanded, it becomes a polynomial about lambda, known as the characteristic polynomial, and its root is the eigenvalue of matrix A. Let's take a specific example. This is a 3 multiply 3 matrix. The first step, A minus lambda times the identity matrix, as shown in the figure. Step 2, find the determinant and obtain the determinant of the matrix A minus lambda times the identity matrix equals 4 minus lambda to the power of 3. Step 3, solve this characteristic polynomials. Therefore, the eigenvalue of matrix A is lambda equal to 4. To sum up the step 4, finding the eigenvalue of matrix R1, write the characteristic equation. The matrix A minus lambda times the identity matrix multiplied by the vector x equals the zero vector. To find the determinant, the matrix A minus lambda times the identity matrix has a determinant equal to 0. Obtain the characteristic polynomial 3. So for the roots of this polynomial to obtain the eigenvalue lambda. That's all. Thank you.
The third part is about the method for finding eigenvector and eigenspace. Now I will introduce how to solve the eigenvector of an n-times n matrix. First of all, we need to clarify what an eigenvector is. For a given matrix A, if there exists a non-zero vector x and a scalar lambda, such that the following equation holds like this, then lambda is called the eigenvalue of the matrix A, and x is called the eigenvector corresponding to lambda. Next, I will explore on the special step for solving eigenvectors. First, starting matrix B, we need to construct a new matrix B, which is defined as B equals A minus lambda I. Among them, I is the identity matrix and lambda is the eigenvalue. The purpose of this step is to transform the problem of solving eigenvectors into a problem of homogeneous linear equation. Second, solving homogeneous linear equation. We need to solving the following homogeneous linear equations, like b times x equals 0. The solution space of this system of the equations is the subspace where the eigenvectors corresponding to the eigenvalue lambda are located. Third, determine the non-zero solution of a homogeneous linear system of equations is the eigenvectors of matrix corresponding to the eigenvalue lambda. It should be noticed that the feature vector must be a non-zero vector because zero vectors are included in the definition. Suppose we have a 2 times 2 matrix A and notice 2 eigenvalues. Our goal is to find the eigenvectors corresponding to these 2 eigenvalues. I have found the following 2 examples to demonstrate to everyone how to solve the eigenvectors of a matrix. Step 1 of finding the eigenvector corresponding to eigenvalues under 1 equals 5. Construct the matrix A minus 5 I equals minus 1, 1, 2, minus 2. Step 2. Solving the homogeneous linear equation system. Step 3. Determine the eigenvectors equals 1, 1, 1. Step 1 of finding the eigenvector corresponding to the eigenvalues 1 equals 2. Construct the matrix A minus 2 equals 2, 1, 2. Step 2. Solving the homogeneous linear equation system. 2 times x1 plus x2 equals 0.2 x1 minus x2 equals 0. Step 3. Determine the eigenvectors. Determine eigenvalues. A2 equals 1 minus 2. For a particular eigenvalues lambda, its eigenspace consists of all eigenvectors plus the 0 vectors. For our example, eigenspace for lambda 1 equals 5 spent 1 minus 1. Eigenspace for lambda 2 equals 2 spent 1 minus 2. The dimension of the eigenspace equals the geometric multiplicity of the eigenvalue. Key point summary of the eigenvectors calculation. Eigenvectors are used to solve non-zero solution of the homogeneous linear equation. 2. The significance of the feature space. The feature space is the solution space of a homogeneous system of equations, which represents the set of volume with invariant direction in matrix transformation. Third, linear combination of feature vectors. Non-zero linear combination of feature vectors are still feature vectors of the same eigenvalues. First, the number of eigenvectors are the linear independence of the multiplicity does not exceed the algebraic multiplicity of the eigenvalues. If the geometric multiplicity is less than the algebraic multiplicity, the matrix cannot be diagonalized.
Let's talk about the plot for properties and series of eigenvalues and eigenvectors. Let's start with 2 key choices related to eigenvalues: algebraic and geometric multiplicity. Algebraic multiplicity means how many times an eigenvalue appears in the characteristic polynomials. Geometric multiples is how many linear independent eigenvectors you can find for that eigenvalue. In other words, the dimensions of the eigenspaces. There is a very important rule to remember. For any eigenvalues, geometric multiplicity is always less than or equal to algebraic multiplicity. If they are equal for all eigenvalues, then the matrix is diagonalizable. For example, the matrix had eigenvalues lambda equal to 1 and lambda equal to 2. For lambda equal to 1, the algebraic multiplicity is 2, but the geometric multiplicity is only 1. For lambda equal to 2, both multiplicities are 1, so the inequality is satisfied in both cases. Now, useful theorem. If a matrix has distinct eigenvalues, then the corresponding eigenvectors are linear independent. This is especially helpful for predicting triangulability. In the example, matrix A has 3 different eigenvalues, 2, 3, and 4. We compute the eigenvectors for each one and check if they are linear independent by verifying that the only solution to C1V1 and C2V2 and C3V3 equal to 0 is C1 equal to C2 equal to C3 equal to 0. We confirm independence. Eigenvalues aren't just abstract, they tell us a lot about the matrix itself. Let's go over 3 major properties. Invertibility. A matrix is invertible if and only if 0 is not an eigenvalue. If 0 is an invertible, the determinant is 0, meaning the matrix is singularly. For example, a matrix with eigenvalues 3 and negative 1 is invertible since neither is 0. Determinant. The determinant of a matrix equals the product of its eigenvalues. This connects the algebraic concave of eigenvalues to a Corey matrix operation. For example, if eigenvalues are 1, 2, and 2, then delta A equal to 1 multiplied by 2 multiplied by 2 equals 4. Retrace. The trace equals the sum of the eigenvalues. This works because of the structure of the characteristic polynomials. For example, if the eigenvalues are 4, 2 is the square root of 3, and 2 minus the square root of 3, the trace is 4, 8, 2, 8, 2 equal to 8. So with eigenvalues alone, we can assess whether a matrix is invertible, conclude its determinant, and confirm its trace. Finally, let's talk about complete eigenvalues, which are also quite common in real matrices. 1. Occur in conjugate pairs. If a matrix is real and has complete eigenvalues, they must appear in conjugate pairs such as A is Bi and A minus Bi. 2. Symmetric created. If a matrix is symmetric, then all of its eigenvalues are real. No complete numbers appears. This is an important result based on Hermite matrix 0. 3. Geometric interpretations. Complete eigenvalues often represent rotations on periodic behaviors, and they frequently appear in fields such as imaginary places, physical and vibration systems. So, although complete eigenvalues involve imaginary numbers, they create very real and meaningful interpretations in practical applications.
After seeing PCA in action, let's quickly review the big picture. We started with linear transformations, then defined eigenvalues and eigenvectors as directions that stay unchanged under those transformations. These concepts allowed us to diagonalize matrices, analyze system stability, and simplify data through PCA. This slide highlights 3 essential theorems related to eigenvalues. The spectral theorem tells us that any symmetric matrix can be orthogonally diagonalized using its eigenvectors. The diagonalization theorem states that a matrix with enough linearly independent eigenvectors can be transformed into a diagonal form. Lastly, the power method offers a simple way to approximate the domain, eigenvalue, and eigenvector. These theorems help us simplify complex matrices and are the basis for many practical applications. Now let's look at how eigenvalues and eigenvectors are used in real life. In control systems, eigenvalues help determine system stability. If all eigenvalues have negative real parts, the system will turn to equilibrium over time. In PCA or principal component analysis, we use these eigenvectors to identify the directions of greatest variance in a dataset, which allows us to reduce its dimensions while keeping important information. In image processing, eigenvalues help extract key features or compare images efficiently. Search engines like Google apply eigenvectors in the PageRank algorithm to rank websites by importance. And in graph theory, the eigenvalues of a graph's adjacency matrix can reveal properties like how connected or conclusive the network is. As you can see, eigenvalues are not just theoretic, they play a critical role in many model technologies. Let's look at how PCA uses eigenvalues and eigenvectors to simplify complex data. First, we start with high-dimensional data and compute the covariance matrix to understand how features vary together. Next, we find the eigenvalues and eigenvectors, which reveal the directions of greatest variance and how much information each direction holds. Then we selected the top eigenvectors based on the largest eigenvalues, keeping only the most informative directions. Finally, we project the data onto these directions, reducing it to fewer deficiencies while preserving the key structure. This makes the data easier to analyze and is widely used in tasks like image compression and pattern recognition. Now, let's wrap up with a quick summary of everything we were covered. We began with the idea of linear transformations, which laid the foundation for understanding how vectors behave under mentioned operations. From there, we introduced eigenvalues and eigenvectors as special cases, directions that they stay unchanged except for a scaling factor. These concepts led us to powerful tools like diagonalization, which simplifies complex mentioned computations, and to practical applications such as system stability analysis, principal component analysis for data reduction, and even algorithms like Google's RagePark. So what's the big picture? Eigenvalues and eigenvectors are far more than abstract math concepts. They give us deep insight into structure, stability, and simplifications. Whether in engineering, physics, or data science, they help us understand and transform the world in meaningful ways. Thank you. I hope this presentation gave you a clearer sense of why eigenvalues matter and how they connect theory to real-world impact.